Have you ever seen one of those AI-generated images? Like, you ask for a photorealistic cat riding a unicorn through space, and boom, there it is. And you just think, seriously,
Oh,
how?
absolutely. Or, you ask a chatbot some really complicated question, and the answer you get back isn't just okay. It's actually pretty insightful sometimes.
Exactly. It really feels like these things are learning, like genuinely learning on their own.
It really does. I mean,
Yeah.
we're way past the old days of coding and every single little rule by hand, aren't we?
Yeah, totally. Now it feels like AI just sort of soaks up information from, I don't know, the whole internet, and then suddenly it's writing poetry or playing complex games or even giving these nuanced opinions.
It makes you wonder what's really happening under the hood.
For sure. And it's not just about cool pictures or chatbots anymore. The self-learning stuff is popping up everywhere. Think about self-driving cars or the recommendations you get on streaming services or even like in healthcare.
Right. It's becoming critical in some fields.
So understanding how AI actually learns by itself, it isn't just a fun thought experiment anymore. It feels kind of essential now.
And that's exactly what we want to dig into today. We're going to try and get past those vague explanations like, oh, it's just complex math.
Da-da-da.
We want to look at the actual mechanics, unpack some maybe surprising findings, and really get a handle on what this all means for you listening.
Okay.
So we'll cover how AI learns from data, how that stacks up against how we learn, look at some real-world examples, but also the limitations, and maybe peek into the future a bit.
And we've got some really interesting concepts to explore, like this idea of token tyranny
hmm
and comparing AI to, what was it, statistical savants, but also tone-deaf toddlers.
That's the one. Intriguing descriptions, right?
Definitely. Okay, so let's dive in. How does this self-learning actually work? Because, yeah, someone isn't sitting there typing in all the facts of the world.
No, not at all. The big shift was moving away from those, let's call them traditional rule-based systems. The ones with endless if this, then that statements.
Right, like old school expert systems.
Exactly. Modern AI, particularly deep learning, takes a completely different approach. It learns by basically being flooded with massive amounts of data and then solving what we could call proxy puzzles.
Proxy puzzles. Okay, tell me more. What's an example?
So think about a big language model, like kind of powering many chatbots today. Training involves feeding it just unimaginable amounts of text, trillions of tokens.
And a token is like a word or
Right.
part of a word.
Yeah, roughly. It could be a word, a subword, even punctuation. This data comes from everywhere. Books, websites, articles, code, forums, basically a huge chunk of the internet.
Okay.
The proxy puzzle it has to solve over and over is simply predicting the next token in a sequence. If it sees the text, the capital of France is, its job is to guess the next token, which is probably Paris.
Okay, so it's like a giant fill-in-the-blanks game, but on a massive scale. How does playing that game teach it that Paris is the capital of France?
It's through, well, sheer repetition and a process called gradient descent. When the model guesses wrong, and it guesses wrong a lot at the start, the system makes tiny adjustments to its internal parameters, its weights.
Like tiny knobs inside the machine.
Kind of, yeah. Billions of them. Each time it's wrong, it nudges those knobs just a tiny bit in a direction that would have made the guess slightly more likely to be correct. So, after seeing the capital of France is Paris maybe millions of times in different contexts.
That connection just becomes statistically overwhelming.
Exactly. It hasn't been told the rule, like a fact in a database. It's just learned the extremely high probability of Paris following that specific sequence of tokens. It's all statistics.
That's still pretty wild. So it's statistical likelihood, not programmed knowledge. There are other examples of this. What do you call it? Self-supervised learning.
Oh, definitely. It's used all over. In computer vision, for instance, a model might get shown an image, but with a piece blanked out. Its puzzle is to predict the missing patch.
Ah, okay.
Or, for audio, maybe you feed it a sound clip with a tiny bit of silence inserted, and it has to predict what sound should fill that gap.
So the data itself provides the answers for the puzzle. It labels itself in a way.
Precisely. That's why it's self-supervised.
Yeah.
No need for humans to painstakingly label every object in millions of images or transcribe every word in thousands of hours of audio.
That sounds way more efficient. So just by trying to fill in these blanks, the AI starts to figure out the underlying structure of images or sound or language.
Exactly. It's constantly trying to predict, making errors, adjusting its internal weights, predicting again. And this relentless process leads to the creation of these things called embeddings.
Embeddings, right. That sounds technical.
It is a bit, but you can think of them like coordinates. Imagine a huge multidimensional map of meaning. Words or concepts that are similar end up closer together on this map.
So king and queen would be near each other. And maybe royalty.
Yeah, exactly. And walking might be near running, or happy near joyful. The model learns these relationships purely from how words are used together in the data. When you ask it a question, it's essentially navigating this meaning map based on the statistical relationships it's learned.
Okay, that meaning map idea helps. So let's compare this to us. How do humans learn? We learn rules, sure, like grammar rules, but we also learn from examples, right? Analogies.
That's a really important distinction, yeah. Cognitive science suggests we learn in, broadly, two main ways. We generalize abstract rules from experiences.
Like, don't touch the hot stove.
Right. But we also learn heavily through analogy, recognizing similarities between a new thing and something we already understand. This analogy making is thought to be key for creativity, problem solving, even how kids pick up language so incredibly fast.
Yeah, like a kid saying, I goed instead of I went. They're trying to apply a rule they've sort of half learned, the ed rule for past tense, but they also just copy phrases they hear.
Exactly.
Yeah.
So the big question with these large AI models is, are they learning more like the rule-based system, or are they more like superpowered analogy machines, just retrieving and blending examples?
Are they figuring out the underlying grammar or just mimicking patterns they saw millions of times?
Well, there was this really neat study recently by Hoffman and colleagues that tried to get at this exact question.
Oh, yeah. What did they do?
They used a language model called GPT-J, and they gave it a clever task. They made up new, non-existent adjectives.
Okay.
And they asked the model to turn these made-up adjectives into nouns. For instance, if they gave it a fake adjective ending in eive, like spective, should the noun be spectivity or spectiveness?
Ah, I see. Because the words were fake, the AI couldn't have seen the answer in its training data. It had to generalize somehow?
Precisely. Then the researchers compared GPT-J's answers to predictions from two different cognitive models, basically, simulators of human learning. One simulator learned by forming rules, the other learned by analogy. Based on similarity to known examples, they called it an exemplar learner.
Okay, so which simulator did GPT-J behave like? The rule follower or the analogy maker?
The results were pretty striking. For straightforward, regular endings, both simulators and GPT-J did fine. But for the trickier, more irregular endings like that hereby or iris example, GPT-J's choices closely mirrored the predictions of the exemplar, the analogy-based model.
Interesting.
It wasn't making clean, rule-based decisions. It seemed to be heavily swayed by how similar the made-up word was to real words it had seen and how those words usually form nouns in its training data.
So it's really leaning heavily on the specific examples it remembers. Did they look at the model's confidence, too? Like how sure it was about its answers?
They did, and this is maybe the most revealing part. They found a super strong correlation between GPT-J's confidence in a particular noun ending and how frequently that specific ending pattern appeared in its training data.
So if alivity showed up way more often after certain adjective types in the training text than iveness, the model would confidently pick alivity even for a brand new word.
Exactly. It wasn't about the variety of examples or finding the most consistent underlying pattern. It was overwhelmingly driven by raw frequency.
That feels different from humans, doesn't it? We tend to weigh different kinds of evidence, not just count frequencies.
It does seem different. The researchers noted that human learners in similar linguistic puzzles tend to value the diversity of examples more, looking for the most general rule rather than just latching onto the most frequent pattern, especially if that pattern is a bit weird or inconsistent.
And did this hold true for bigger models too, like the really powerful ones?
Apparently, yes. They mentioned that even larger models like GPT-4 seem to show a similar bias, overvaluing frequent but maybe unusual examples found in the data.
Wow. So the big takeaway is these super smart language models are maybe less like uh, expert grammarians applying abstract rules.
And more like, quote, stochastic parrots with elite pattern-matching memories. That's how the researchers put it.
Stochastic parrots. I like that. Meaning they're brilliant mimics and pattern matchers, heavily reliant on storing and recombining the examples they've ingested.
That seems to be the picture emerging. And this heavy reliance on frequency, this elite memory, for examples, has some really important consequences, which leads us to this idea you mentioned earlier, the token tyranny.
Right, token tyranny. It sounds ominous. What's the core idea there?
It's basically doubling down on that finding about frequency. It refers to that extremely tight link, that high correlation we just talked about,
Yeah.
between how often a pattern appears in the training data and the model's tendency to reproduce it. Frequency rules.
Okay, so if something appears a lot in the training data, the AI assumes it's important or correct, even if it's, total nonsense.
Pretty much. And you see weird effects because of this. For example, you might find a language model confidently repeating some obscure urban legend as if it's established fact,
Why?
simply because that legend got repeated thousands of times on forums or websites that were part of its training data. The model doesn't have a truth filter, it just registers high frequency.
Huh. That's worrying, especially for misinformation. I remember reading about image models having similar issues, right? Like always identifying huskies as wolves if the training photos mostly showed huskies in snow.
Exactly the same principle. The model learns a spurious correlation. Husky image plus snow background, he's a wolf. It latches onto the statistical co-occurrence, not the actual defining features of a wolf versus a husky.
So fixing biases or weird outputs in these models isn't just about better algorithms, it's fundamentally about managing the frequencies in the data they learn from.
That's a huge part of it. Curing bias often means carefully curating frequency. You might need to actively downweight harmful stereotypes or misinformation, even if it's frequent online, and deliberately upsample data representing marginalized groups or less common but accurate information.
It's about consciously shaping the statistical landscape the AI learns from.
You got it. And this frequency obsession also makes it really hard to understand why a model gives a particular answer. If you ask it for its reasoning, the true answer is often buried in those statistics.
Hmm.
Well, this token sequence had the highest probability based on millions of similar contexts in my training data.
Which isn't a very satisfying or human-like explanation.
Not at all. It's opaque. The reason is a complex function of frequencies across billions of parameters, not a logical step-by-step deduction.
Okay, so we've talked a lot about language, but this self-learning idea, these proxy puzzles and statistical patterns, it applies beyond text, right?
Oh, absolutely. The same core ideas pop up in many different domains. Take computer vision again. Models like DynoV2 use something called contrastive learning.
How does that work?
Basically, you show the model two different, maybe slightly altered views of the same image, and you teach it to recognize that these two views represent the same underlying thing. You also show it views from different images and teach it that those are different.
Ah, so it learns similarity without needing labels like cat or dog.
Exactly. It learns visual features, edges, textures, shapes, just by comparing pixels to pixels. Over time, it builds a rich understanding of visual structure.
And that's how it can learn artistic styles, maybe? By seeing patterns across many paintings?
Sort of, yeah. It identifies recurring visual patterns and look at speech models, like Whisper. They process huge amounts of audio, often multilingual. They learn partly by predicting the next little slice of audio waveform, but also by aligning the sounds they hear with corresponding text transcripts when available.
So it's learning both the sound patterns and the link between sound and text.
Right. This dual task helps it learn phonetics, accents, different languages, speaker characteristics, all without explicit programming of linguistic rules.
And then there's reinforcement learning, like AlphaGo Zero playing Go. That wasn't trained on human games at all, was it?
No, that's the amazing thing. It started knowing only the basic rules of Go and then just played against itself millions and millions of times.
Wow.
Through trial and error, figuring out which moves led to winning positions, it developed strategies that surpassed centuries of human Go knowledge. It even discovered moves humans had never considered.
That's incredible. So across language, vision, audio, games, the pattern is define some kind of self-prediction task or a game, give it feedback, and let the learning algorithm optimize based on that feedback.
That's the essence of it. And through that process, these models develop internal representations, those embeddings or weights, that capture complex patterns and sometimes lead to surprisingly abstract abilities.
It really is amazing how simple loops can build such complexity. So where is this actually being used now, like out in the real world, beyond the research lab?
It's increasingly widespread. Think about dynamic pricing airlines, ride-sharing apps.
Right, prices surging when demand is high.
Yep. Exactly. AI analyzes historical demand data, recognizes patterns similar to past surges like during holidays or big events, and automatically adjusts prices in real time. No human needs to manually tweak things constantly. It's learning from past demand patterns.
Okay, that makes sense. It's seeing an analogy to past situations. What else?
Recommender engines, streaming sites, online shopping, they're constantly learning your preferences.
Based on what I click on or watch?
Yep. Your behavior teaches the AI.
Mm.
If it sees that people who like movie A often also like movie B, it learns that association and starts recommending movie B to others who watch movie A. It's unsupervised pattern finding.
And it happens automatically behind the scenes.
Totally. Then there's fraud detection in banking. Instead of just using fixed rules for suspicious activity, AI can learn the patterns of normal transaction behavior for millions of customers.
And flag anything that looks weirdly different.
Exactly. It identifies anomalies, things that don't fit the learned patterns,
Yeah.
often catching sophisticated fraud that rule-based systems might miss. It learns normal by itself.
That's a really useful application. Any others?
Well, we're starting to see things like autonomous labs in science. AI can design experiments, control robotic equipment to run them, analyze the data, and then decide what experiment to run next, optimizing for discovery.
Wow, AI-driven science. And you
Yeah.
mentioned code generation earlier, like GitHub Copilot.
Yeah, that's a great example. It's trained on vast amounts of code from GitHub.
Yeah.
When you start typing, it suggests completions, sometimes whole functions,
How does it learn new programming tricks or libraries?
just by seeing them used in the code examples it was trained on. If a new popular library emerges, Copilot learns its patterns and how to use it simply because developers start using it in the code it ingests. It learns by example.
So the big picture here is a shift, right? Instead of engineers meticulously writing logic.
The focus shifts more towards designing the learning process, curating the right data,
Yeah.
setting up the guardrails, and monitoring the output. The value is in managing the self-teaching process, not just writing code.
Understanding how it learns becomes key to using it well.
Exactly. And that also means understanding its limits and risks.
Right, because it's definitely not perfect. We've touched on some issues, but what are the main pitfalls we need to watch out for with self-learning AI?
Well, that bias issue is a big one. We talked about token tyranny leading to weird outputs, but the more serious concern is bias osmosis. AI learns from data created by humans, and that data contains all sorts of societal biases.
So the AI just learns those biases as statistical patterns.
Precisely, like a hiring algorithm trained on past data reflecting historical gender or racial biases, might learn to replicate those biases. Even if the bias characteristics aren't explicitly mentioned, it picks up on subtle correlations.
That's deeply problematic. What else?
Spurious correlations, which we mentioned with the huskies and snow. The AI finds a pattern that holds true in the data but doesn't reflect reality or causality. Think of a medical AI linking watermarks on X-rays to disease because certain hospitals use watermarks and also treat sicker patients.
It connects unrelated things just because they appear together frequently.
Right. And then there's the opacity problem again. It's hard to know why it made a decision, even if it gives you an explanation, because the real reason is buried in those complex statistics. Debugging or trusting it becomes challenging.
Yeah, that lack of transparency is tough. What about data needs?
They are incredibly data hungry. Humans can often learn a concept from one or two examples. Current AI often needs millions or billions. This makes them less flexible and prone to errors or hallucinations when faced with truly novel situations not well represented in their training data.
They struggle without enough examples. And you mentioned reward hacking before, for reinforcement learning.
Yes, that's when an AI, trying to maximize a reward signal we gave it, finds a loophole or an unintended shortcut. Like an AI designed to win a boat racing game might learn to just spin in circles hitting turbo boosts because that racks up points faster than actually finishing the race.
Huh. Okay, so it achieves the goal, but not in the way we intended, and possibly with negative side effects.
Exactly. These aren't trivial problems. They're kind of inherent to the way these systems currently learn. It requires constant vigilance, careful design, robust testing, and often keeping humans in the loop.
So pure autonomous learning is still a ways off. We need careful management.
Definitely. Which leads to the question, what's being done to make AI learning better? More efficient, maybe more human-like?
Yeah, are researchers trying to bridge that gap between statistical pattern matching and, deeper understanding?
Absolutely. There's a ton of research in this area. One exciting direction is meta-learning.
Learning to learn.
Essentially, yes. Training AI models not just on one task, but on how to adapt quickly to new tasks with much less data. Trying to mimic that human flexibility.
Oh, okay, that sounds useful. What else?
Trying to get AI to understand causality, not just correlation. If AI could grasp cause and effect better, it might avoid those spurious correlations we talked about.
Right, understanding why snow and huskies appear together, not just that they do.
Exactly. Another area is intrinsic motivation, building AI with the kind of built-in curiosity, encouraging it to explore and learn actively, not just passively optimizing a reward.
Like a curious child exploring the world?
Kind of. And multimodal learning, training AI on text, images, sounds, maybe even touch, all at once. The idea is that grounding concepts across different senses might lead to richer understanding, like how we learn.
Connecting the word dog to the image of a dog and the sound of barking.
Precisely. And finally, continual learning, trying to solve the problem of catastrophic forgetting, where an AI trained on a new task suddenly forgets everything it learned before. Humans accumulate knowledge. We want AI to do that too.
So the goal is to move beyond just scaling up data and computation towards more efficient, flexible, and maybe grounded learning.
That's the hope. Progress in these areas could lead to AI that learns faster, needs less data, and is potentially more reliable and understandable.
Okay, that's the research frontier. But for people working with or using today's self-learning AI, what are the practical takeaways? How can we steer these systems better, knowing what we know now?
Well, given how much these models rely on examples, that analogy-based learning, the most crucial thing is deliberate data curation. Really think about the examples you're feeding the AI.
Be intentional about its education, basically.
Exactly. Don't just dump data in. Consider its quality, diversity, and potential biases. And remember, the token tyranny, actively manage frequencies.
Right, downweight the bad stuff, maybe boost the good, underrepresented stuff.
Precisely. For safety-critical applications, don't rely solely on the learned patterns. Blend in explicit rules or hard constraints as safety nets.
Use the statistics, but have some non-negotiable boundaries.
Yeah, and monitor behavior over time. Use diagnostic tests or prompts regularly to see if the model's performance is drifting or if it's learned something unexpected or undesirable.
Keep checking its homework.
Kind of. And incorporate human feedback. Tools that let users flag bad outputs or provide corrections are incredibly valuable for fine-tuning and aligning models with human norms and expectations.
So keep humans in the loop for refinement.
Definitely. Also, try to get the model to signal its uncertainty. An AI that can say, "I'm not sure about this," is often much safer than one that confidently makes stuff up.
Confidence scores are equivalent. Good point. Anything else?
Document your data sources. Know where the training data came from. This is vital for traceability, debugging, and understanding potential biases down the line.
It really sounds like managing self-learning AI is becoming a discipline in itself.
It is. It requires a shift in thinking from traditional programming to becoming more like a careful curator, educator, and monitor.
This has been super insightful. So if we had to boil it down, the main message about how AI learns by itself today is
I'd say the core idea is that current AI, especially large models, operates primarily as a voracious pattern librarian. It learns by ingesting vast libraries of examples, weighting them by frequency, and then making sophisticated statistical analogies.
not necessarily by deriving abstract rules like we might.
Less so, it seems. It's more about incredibly powerful pattern matching and retrieval, guided by the statistics of the input data.
And knowing that changes how we should approach AI, doesn't it? Puts a huge emphasis on the data.
Absolutely. Data quality, data balance, data curation, these become central concerns for building reliable and fair AI. Understanding why an AI does something often means tracing it back to the influential examples in its training, not searching for an explicit rule it learned.
We're still figuring out how to best manage this powerful but different form of learning.
We definitely are. But the research is moving fast, trying to make AI learning more robust, efficient, and maybe even a bit more human-like in its adaptability.
So when we see AI do something amazing, we shouldn't just think magic. We should think massive data plus clever pattern finding and realize that we're all involved in creating that data.
That's a great way to put it. It shifts us from just being amazed observers to being, in a sense, active participants. We are all contributing to the data streams that teach these AI systems.
We're like co-teachers.
In a way, yes.
Mhm.
We're collectively writing the syllabus of the digital information we create and consume.
Yeah.
It really makes you think about the kind of knowledge and, maybe implicitly, the values we're feeding into these learning machines.
Passive awe turns into active responsibility. A lot to think about there.